So our next speaker is Cambyse Rouzé, who's going to tell us about dissipative Gibbs sampling. Let's welcome the speaker.
Thank you very much for the kind introduction. I also like to thank the organizers for giving me the chance to present this work, which is a joint work with Alvaro Alhambra from Madrid and David Perez Garcia from Copenhagen. So in this work, we were interested in better understanding regimes where one can hope to find efficiency in trying to understand thermal properties of many-body systems. So for me, a many-body system will be just a system made of many qubits, which are lying on some lattice, on the vertex of a lattice. And I will assume further than only qubits which are neighboring each other will interact at once. Okay, so for this, I can then describe the Hamiltonian of the system to be just a sum of local terms, and they will be of order n of them, n being the number of qubits. Then, once you're given the Hamiltonian, you can start talking about Gibbs states, which we have already heard a lot about in the last 3 days. So this will just be a convex combination of energy eigenstates with weights given by this Boltzmann constants, exponential minus beta e, beta being the inverse of the temperature. And to make this a state, you have to obviously properly normalize it by its partition function, which is also something that physicists actually want to approximate efficiently. And what we were interested in here was not so much, or it was also about approximating partition functions, but also about actually preparing the Gibbs states themselves. Okay, so we're interested in this Gibbs sampling task, which is defined as follows. You're given as input the interactions of your system, which form your Hamiltonian, the inverse temperature beta, and some approximation parameter epsilon. And what you're required to do is to output a state on the quantum computer, sigma tilde, which you can promise to be epsilon close to the Gibbs state corresponding to those parameters in trace distance. Okay, so this is what we care about. And since we know that once we have access to those states, we can actually approximate partition functions. And since, as we heard in the previous talk, approximating partition functions is actually hard in general, one should not be able expect that one can always do this. So what we cared about was to find regimes for which we can actually do this efficiently. And another question that we also wanted to try to better understand is whether Gibbs sampling is a strictly weaker notion of computation, or if it actually offers as much power as universal computation. So to answer this question, we essentially have a bunch of results which nicely split into a low temperature and high temperature regime. I will start with the high temperature regime. So at high temperature, we can show that for a general class of local Hamiltonians, potentially non-commuting here, there will exist some threshold temperature that will depend on the locality of the problem, which will be constant, and above which one can show that a certain type of Gibbs sampling algorithm converges in optimal way, so in time n log n over epsilon. So as I just said now, this is the first proof of optimality of this kind of Gibbs sampling algorithms for a very general non-commuting class of Hamiltonians. And as a simple corollary, we can use this Gibbs preparation algorithm to approximate partition functions, again, above this threshold temperature. And we actually prove a runtime for this problem of order n to the cube divided by epsilon squared. Okay? So this is the high temperature regime. And at low temperature, what we can show is that one can always encode output states to quantum circuits, say made of capital N gates, into a Gibbs state at very low temperature, that one can actually show that the same Gibbs sampling algorithms that we used at high temperature will also converge in polytime. Okay, so what this essentially tells you is that Gibbs sampling is actually giving us a new universal model of quantum computation in that sense, which is equivalent to the circuit model and equivalent to other models, for instance, adiabatic quantum computation. The difference between Gibbs sampling and adiabatic models of computation, of course, is that in the latter, you change the Hamiltonian throughout time. So you run this Schrödinger equation, time-dependent Schrödinger equation that interpolates between simple Hamiltonians and the one for which the solution to your problem has been encoded. Whereas in this Gibbs sampling regime, we just fix the Hamiltonian beforehand, and we just have to cool down the system at low enough temperature to get the solution. I should also mention at this point that this was highly inspired by previous work by these authors here, where they showed something very similar. They consider also a way to map quantum circuits into ground states of Hamiltonian, which can be assessed by essentially cooling down the system locally using certain types of Gibbs sampling algorithms as well. But then what they had to do in this paper was to, at each step of their algorithm, they had to measure the energy of the circuit to ensure that it was actually getting lower and lower. So the difference with this and what we do is that we don't need to do these mid-circuit measurements. We just have to cool down and wait until we reach the equilibrium state. Another small difference also is that the temperature range that we get is slightly higher, but still of very high order. OK, so now let me tell you which algorithms we actually use to prove this bunch of results. So this is an algorithm that was devised in this first paper here by Chen, Cascareno, and Gillian 2 years ago, which relies on this continuous time Lindbladian evolutions, which we have already seen in many talks till now. So the generators can be defined as sums over terms, k being just labeling a site in your lattice. And those, what you can think of as local terms, these LKs, they are defined in terms of certain jump operators, which in my case will be just a time average of single qubit parity jumps, Sk. So it can be either sigma x, sigma y, sigma z on each of the lattice sites, which you first evolve according to the Hamiltonian evolution, and then integrate over some rapidly decaying function, which you have to choose properly. And the nice thing about this algorithm is that you can actually show that for those Lindbladians, you have the detail balance condition, meaning that or implying that the Gibbs state is the unique fixed point of your evolution. And at the same time, you can show that those evolutions can be efficiently implemented on a quantum computer, because it has two very nice properties. What we also add to the mix here is that since we are looking at local jumps to start with, we can very easily localize these generators to operators which only act on neighboring qubits for each site k. Okay, so we're just using Leibnizian bounds to prove this kind of bounds. And now let me give you the idea of how we actually show this high temperature argument. So for this, we have to devise what I would call a gradient estimate proof. So what we want to do is to control this trace distance between the state rho at time t. You initialize the system at any state, and you want to control the trace distance between the state and the Gibbs state, the infinite time limit, which by the rational formulation for the trace distance can be easily shown to be controlled by this norm between an arbitrary observable x, boundary observable, that you evolve up to time t, and its average with respect to the max-min mix state. Okay, so this is a bit quite easy to see, which means that if we want to control the mixing time, it's enough to control exactly when this norm gets small. Okay? So let's try to build intuition for what this upper bound actually tells us about, starting from the classical setting. So classically, let's say we have some dissipative process, some Markov chain, on some configuration space, and we look at one observable of the chain, so some function of the parameters. And before we initialize the process, the function can be extremely oscillating as a function of those parameters. And then as we initialize the process and time goes by, we see that the function will essentially slowly smoothen until it actually reaches its average with respect to the fixed distribution of the chain. Okay? So intuitively, it seems like if we want to control the time it takes for this to happen, it may be enough to actually control some sort of measure of regularity of the function, say the Lipschitz constant of the function. And these ideas have been successfully applied in many other places. I just want to mention 2 places here. So if you want to consider, say, heat semigroups or Brownian motions on compact Riemannian manifolds, you can actually show that the rate at which these kind of gradients converge is directly dictated by the Ricci curvature of the manifold. So there is really a geometric aspect to it. And some other example that is a bit closer to what we care about today is this Glauber dynamics for Ising or Potts models on arbitrary graphs above a certain threshold temperature. So for those ones also, you can show that these discrete Lipschitz constants are also exponentially decaying. Okay? So now if we want to repeat these ideas in the quantum setting, I first have to give you an idea of what would be the replacement for these Lipschitz constants. And what we worked with was the oscillator norm of an observable. So it's defined as the average over all the qubits of the lattice of the operator norm of what I would call a quantum gradient applied to the observable, corresponding to the ith qubit, where this quantum gradient is essentially measuring how far the observable is from not depending on the ith qubit. Okay, so I just removing here so you take x minus, this, replace the channel that replaces x by the maximum mixed state on the ith qubit. So this oscillator now has some nice properties, the first of which being that it's equal to 0 if and only if the observable is a constant multiple of the identity, which already tells us that maybe this is a good measure to control how fast you converge to equilibrium. And another nice property is that you can use this to bound from below and above quite tightly this operator norm that we started with. Okay? So using this bound, then you can see that the mixing time, the time it takes for the chain to converge, will be controlled by the time it takes for this oscillator norm to get epsilon over n close to 0. Okay, so that's what we now want to prove. And let me give you some intuition for why this can be done first in the simplest setting, where we just are at infinite temperature, so there's no interaction in the system. The system just thermalizes to the maximum mixed state in this case. And these evolutions I have been telling you about, in this case, will also reduce to just single qubit depolarizing semigroups, acting on each of those qubits independently at random, independently from the others. This is just the channel that you end up with for each of those qubits. It will essentially very quickly replace the initial state rho by the maximum mixed state. And now if you compute the gradient on observables which are evolved according to this evolution, you see that since the gradient is, has identity as in the kernel, this gradient will also exponentially decay with a rate of 1 over n. Okay? Which also means that the oscillator norm itself will exponentially decay with a rate of 1 over n. And then if you plug this into the bound I gave you for the mixing time before, you see that we get this n log n behavior that I promised. Okay, so this is infinite temperature. Let's see if we can lower the temperature down. And for this, we relied on some well-known condition or criterion that was devised by Dobrushin back in the 70s, who was studying, in this case, the thermal properties or equilibrium properties of classical lattice spin systems. And in his study, he came up with this criterion, which depends on two maps. So one map, this nabla k, is just a discrete gradient that acts on each bit at a time. And then you have this other map, ej, whose action is essentially to thermalize the system on the jth side. Okay? So more mathematically, ej is just a conditional expectation which maps functions to the average with respect to the Gibbs distribution, conditioned, so on the jth side, conditioned on the values of the spin outside of this jth side. Okay, so now if you look at k and j, and you take k to be far away, by far away I mean that it should be not in the interaction range of the jth side, then you see that this commutator here is just equal to 0. So this criterion is always satisfied for those cases. What becomes more complicated is when k actually is within the interaction range of j. So the Dobrushin criterion tells you that if this is small, which would depend, of course, on the Hamiltonian you're looking at, or the temperature, then, in fact, you can show that the Gibbs distribution satisfies nice properties. It decays, the correlations decay exponentially, and so on. So this is really just, at this point, thermal properties. But this was later on mapped to dynamical properties of those systems, first by Eisenmein and Hulli in the 80s, and then later on by Stilck and Zangaliski. And this author realized that under the same criteria, you can show that for a very specific evolution generated by these maps, which directly depend on these conditional expectations, you recover this exponential convergence of the Lipschitz constant. Okay, so again, this with a rate of 1 over n. So I should at this point also mention that these ideas have been already successfully applied in the quantum setting in these papers. However, the authors here only consider commuting Hamiltonians. And it wasn't clear how to further extend them to non-commuting Hamiltonians. So let's see how we did. What we came up with was a slight change of this Dobrushin criterion. So the issue with the previous definition was that, remember we had this conditional expectation that was lying here. We can still define conditional expectations in the fully non-commuting setting, but it turns out that this map is very difficult to control because it would be essentially supported everywhere on the lattice, and it's not clear how you would actually be able to prove this condition. So instead, what we did was to replace it by the generator itself, LJ, which I mentioned already before, has nicer properties, can be localized in a nice way. This was coming at the cost of having to add one more criterion. So we have to also assume that locally, these generators are very close to the infinite temperature limits. That's one more criterion we had to add. But with these two conditions, we can show that, again, this oscillator norm in this fully quantum setting will also decay with a rate of 1/n. OK, so now the last question is, when is this actually satisfied? And as I already promised before, we can show that these conditions are indeed satisfied above a certain threshold temperature, which will depend on the dimension of your lattice, essentially, as well as the locality of the Hamiltonian. And the idea I already mentioned 2 times. So the idea is really to essentially show that these generators Lj are nicely localizing using Lieb-Robinson bounds. And once you localize them, you see that many of those quantum gradients will be actually commuting with those generators. So the only thing you have to control is what happens when k is very close to j, but you can also do this. OK, so let me also give you some comparison to other methods which we have actually heard about over the morning. So this morning, we've seen that this very nice work by Bakshi et al., where they also come up with an efficient quantum algorithm for the preparation of quantum Gibbs states. But the way they came up with this algorithm is very different from the one that we're using. So we're using Lindbladian dynamics, whereas they were first showing that high-temperature Gibbs states are not entangled, and this was allowing them to use other methods to show convergence of their algorithm. The methods that they are using, which are known as cluster expansion methods, were already known beforehand, and they are very useful in trying to approximate partition functions. They also give you efficient runtimes to approximate partition functions at high enough temperature. However, these runtimes, very often, these polynomials, they have a high exponent that you have to also keep track of. Whereas in our case, when we use our Gibbs sampling algorithm to approximate partition functions, the runtime has this very nice polynomial form. Okay? And one last thing I would also like to mention is that it's not clear whether the temperature ranges that we can get with our methods, how do they compare with the ones of these other papers. So it's maybe that we are assessing Gibbs states which are not separable, but it's not yet clear. So it requires more work to check this. And before I conclude, let me also mention these two new papers that appeared in January, where using essentially the same Lindbladian dynamics, people have managed to show that in the case of not of qubits, but of fermions, at any temperature for certain Hamiltonians which are approximating free fermion systems, you also have efficiency in the runtime of these algorithms. All right, so as an outlook, I think I still have just a few minutes. There are still many questions that we still want to assess. The first one being, can we improve over this inverse temperature at which we don't know whether our method works or not? Again, whether we can connect our threshold temperature to separability is also unknown. And what would be really nice would be to find some non-perturbative condition under which we can also show that these chains converge fast. So far, we always either perturb height in the infinite temperature regimes, or we perturb nice Hamiltonians. But if we could find some criterion under which we can show efficiency, that would be really, really nice as well. So this is for the high temperature regime. And for low temperature, we'd also like to understand what kind of circuits we can actually assess by looking at Gibbs samplers at higher temperatures. So far, we have to assume that the temperature is of a very high polynomial degree, for which we know that we can approximate any quantum circuit. But what happens if you take log n, beta of order log n? Can we still get something interesting? And also, of course, whether we can find some robustness in these methods compared to the circuit model of computation. All right, so with this, thank you for your attention.
Nice talk. We have time for questions. Here.
Thanks for the nice talk. In your definition of geometric locality, you had, I guess, just a technical assumption that the operator norm of each of the terms in the Hamiltonian is less than 1, which I think just sets your units of time and energy, basically, right? Could you make more? Would you get better results if you had more structure, for example, that like all of the terms had approximately the same operator norm or something like that?
So our proof technique doesn't really care about the structure in that sense. Of course, the bound depends on the locality, right? So if you're more local, it becomes harder, and the temperature gets higher, the threshold temperature. Whether we can use nice structure, maybe, but it's unclear.
Presumably, if it was like actually translation invariant, you should be able to do better at least.
Yeah, I mean, this, of course, in 1D, we would expect that this is always efficient at any temperature. We still cannot do this, but yeah.
Thanks.
Thanks for the talk. I have a question for your quantum dual-branching condition. So you define your gradient operator to be identity times the replacer channel to maximally mixed state locally, right? So do you think it can be generalized to generalized to some other type conditional expectations, or do you think it can help in some other cases?
Yes, I mean, this is because we're assessing high temperature, so it makes sense to take those ones, because at infinite temperature, you can show the decay using those ones very easily. But if you have some other models in mind, of course, you could use other gradients that may also be helpful, yes.
Thank you. What's the challenge of extending the one-step bound to sort of taking a larger region and thereby being able to assessing lower temperatures?
We tried, and we didn't manage, so that's the challenge. Yeah, I think the issue is really this other condition that we have to assume that we are close to high temperature already, remember, with this single K bounds. This is something you don't have in the classical setting. And it sounds like because of this, you have to always assume that you're at high enough temperature. But maybe it's something you can remove. We just haven't managed to do this.
Yeah, thanks for the very nice talk. So in both the classical and quantum dual-branching conditions, the idea seems to be that you can control the oscillation or gradient direction by direction. They're sort of independent, right? I mean, the others are perturbation. This is maybe some inherent easiness going on there. So, because not all the thermalization optimization problems can be done with direction by direction. So I just, of course, the quantum side has just started, but wonder whether there's some lessons to be learned in the classical literature that goes beyond this direction by direction control.
You mean whether we need all the directions or? Yeah, I think in the diffusive setting, people have been trying to do this in the classical case. I'm not very aware of the literature, but there are some results there. Yeah. For sub-Laplacians, I think there are some things.
I think time is running up, but if you have more questions, feel free to reach out to the speaker and let's thank him again.